Hello. We continue to work with you on the topic of friction force, and today we have another problem. A bar is sliding on an inclined plane with an angle of inclination of 30 degrees. The coefficient of sliding friction between the bar and the plane is 0.3. With what acceleration will this bar slip? For how long will it slip from the given plane, if its length is 2 meters? So, let's write down the conditions of the problem. It is necessary to determine the acceleration of the given bar and the time of its slipping. Let's write down the data that we know. The angle of inclination of this plane to the horizon is 30 degrees. The coefficient of sliding friction is 0.3. The length of this plane, denoted as L, is 2 meters. To solve this problem, we will need a drawing to show how and in what direction the forces will act when it slips. And consider the laws that we will use in solving such a problem. The first force we will consider is the force of gravity acting on this bar. Next is the force of the support reaction. Recall that it will always act perpendicular to the surface that this body is on, and there is friction slip between the surface and this body. This frictional force will impede the motion of the given object and create certain obstacles. We will use the law of kinetic friction for this force, which will affect the acceleration that the given body acquires as it slips. What to do if we meet with such a problem and we see that the given forces are a little bit out of our usual coordinate axis? For such a solution, we can apply coordinate axes that will be more related to the plane itself than to the surface of the Earth. To do this, we can have the x-axis along the coordinate axis parallel to the given plane and the y-axis perpendicular to the given plane. What is the purpose of this? In order for us to consider with you the maximum number of forces that will fit into the given coordinate plane. Well, if there is some force that acts at an angle to these axes, we will take some components accordingly. So let us now consider the equation of motion for this body in vector form. For this purpose we use Newton's second law. Taking into account that the product of the mass of the body by its acceleration is equal to the sum of all the forces acting on the body. In this case, 3 forces act, and together they produce this acceleration of the bar. Next, our task is to consider this equation in terms of its projection on the x-axis and on the y-axis. For this purpose, we use certain relations, considering the fact that we can calculate the component of gravity acting along x and the component acting along the axis. Y. And given these forces, let's rewrite this equation in projection on the respective axis, which is obtained along the x-axis. The acceleration has a positive sign, so let's leave it with a plus sign. Further down, the positive projection of the force of gravity on the x-axis acts downward and the friction force acts with a minus sign. The support reaction force goes to 0 in this case because it acts perpendicular to x. Further, what is obtained along the y-axis? There is no acceleration along this axis, and we see that the support reaction force has a positive sign of its component, and the gravity component along the y-axis has a negative sign. We get a system of 2 equations, which we need to solve. For this purpose, let's describe as much as possible what we can describe here. For this purpose, of course, we must take into account that this angle theta will be in this triangle. That is, it will be located between the force of gravity itself and its component on the y-axis. And then we get that the component along the x-axis is the opposite cathetus for this angle. And with that in mind, let's replace component on the x-axis by the product of the gravity itself and the sine of the given angle. Next, let's write the friction force, which is the product of the friction force, of the force of friction by the force of the support reaction. Then from the second equation, we get directly what the support reaction force itself is to put it into the friction force. This is the y component of the force of gravity. So you and I should probably even remember that if you express one component through sin, the second component will automatically be expressed through cosine. You can see from the triangle that this is the adjoining cathetus to the given angle. It remains to solve the resulting system and get the answer. The product of mass on acceleration, that would be the force of gravity, which is the product of mass times the acceleration of free fall, by the sin of the angle and minus the product of the kinetic coefficient of friction. Here we see that instead of the support reaction force, we're already substituting the entire component of gravity, taking into account its substitution. We have received such expression, and here we see that the mass of the body in all summons is present. That is, we can reduce the mass in all parts of this equation, and in fact we immediately get the answer to our question: what is equal to the acceleration of this body? The acceleration of free fall can be taken out of the bracket as a general multiplier. Then in the bracket remains this expression. That's our final formula. So we just need to put a numerical value on it. The sin of 30 degrees, I remind you, is 0.5 tenths. Minus the coefficient of friction is 0.3. And the cosine of 30 degrees is approximately 0.87 hundredths. So after the calculations, you and I get a value of 2.3 tenths of a meter per second squared. All in all, for this motion, that's a pretty normal answer. Well, in order to estimate the time of slipping of this body, we now have the acceleration with which this body moves. We have calculated it. We know the length of the plane. Well, and the task itself was clear, that the bar begins its movement from a state of rest, so it will be most convenient to use the formula for calculating the movement of the bar, taking into account the initial velocity and the acceleration it has. Our well-known law of time dependence of displacement. Now this part of it goes to 0. So we're left with this expression. So L is at squared divided by 2, hence time is the square root of 2L divided by A. So by putting a numerical value on it, we get the approximate answer, 1/3 of a second. So we've solved the problem by taking into account that the forces that act on this body can be located at different angles to each other. And here it is very important for the most comfortable solution of the problem to try to choose the coordinate axis correctly. Although I can say that, of course, the choice of coordinate axis does not depend on how you will further solve the problem in terms of the answer. That is, the answer will be exactly the same. You will decide if you are in this coordinate plane or arrange the coordinate axis, as we usually used to do. Of course, the answer will not depend on this. Will depend only on the convenience of solving this problem. So this is the end of our practice. See you in the next lessons. Goodbye.